Have you ever looked at a tiny little battery and wondered how in the world it can power something that needs way more voltage? Well, the secret is this really clever device called a boost converter. It takes a low voltage and it just steps it up, sometimes by a huge amount. It honestly feels like magic, but today we're going to pull back the curtain and see exactly how this incredible trick is done.
Right, so here's the core puzzle we're tackling. How can a single little 1.5-volt battery, something you have in your junk drawer, create thousands of volts? I mean, it seems like it should be impossible, right? But the answer isn't magic. It's just some really elegant physics. And what's truly incredible is that the heart of this whole thing uses just 3 super basic parts: an inductor, a capacitor, and a switch. That's it. Our goal here is to figure out how these simple little components can team up to do something so extraordinary. So here's our game plan for unpacking all this. We'll start with the puzzle itself, then we'll use a really simple water analogy to kind of build our intuition. From there, we'll translate that into an actual circuit, see how a simple switch gives us total control, perfect the design, and then finally, we'll look at the surprisingly simple math that makes the whole thing tick. Okay, so the fundamental puzzle is this. How do you get more voltage out than you put in? It sounds like you're breaking some kind of law of physics, like you're getting something for nothing. But the secret isn't creating energy out of thin air. It's all about storing it and then releasing it in a very specific, very clever way.
To really truly get this, let's just forget about electronics for a minute. Let's think about something we all understand: water. This analogy with a simple pump and a big, heavy flywheel is absolutely the key to understanding this entire concept. Trust me.
So imagine you've got this little water pump, and it's connected to a cylinder with a weighted piston on top. Now, this pump has a hard limit. It can only push with 10 pascals of pressure. As soon as the pressure from the piston's weight matches that, the pump just can't push any higher. It's stuck. So how do we lift that piston even further? Well, the trick is to add a big, heavy flywheel into the pipe. As the pump works, it doesn't just push the piston, it also gets that flywheel spinning, storing up a ton of energy in its momentum. Now here's the cool part. Even when the pump hits its 10 pascal limit, the flywheel's inertia just keeps on going. It keeps pushing water, forcing the pressure past the pump's maximum. But then, that higher pressure on the piston side starts to push back, and you get this sloshing. The energy oscillates, sloshing back and forth between the flywheel's motion and the piston's pressure. Okay, you got that physical picture in your head? The pump, the piston, the sloshing flywheel? Good. Because now we're ready for the big leap. Let's translate this entire water system into its electrical equivalent. This is where it's all going to start to click. Here's the one-to-one translation. The water pump, our source of steady pressure? Well, that's our battery, a source of steady voltage. The big, heavy flywheel, storing all that momentum? That's our inductor, which stores energy in a magnetic field. And the weighted piston, storing potential energy as it gets higher? That's our capacitor, storing energy as an electric charge. It's a perfect match. So the most important thing to get here is this. An inductor resists a change in current, just like a heavy flywheel resists a change in speed. And a capacitor's voltage goes up as you stuff more charge into it, just like the piston's pressure rises as you push more water under it. They're direct energy-storing analogs. But remember that sloshing, oscillating system? I mean, that's not very useful by itself. To turn this whole concept into a practical device, we need to take control. And we're going to do that with the most important part of the whole circuit, a simple little switch. Because here's the problem we have to solve, right? In our water analogy, the flywheel pushes the piston up, but then the piston immediately pushes back down, pulling all that energy right back out again. The energy just sloshes. So how do we stop that? How do we make each push a permanent gain, ratcheting that voltage higher and higher and keeping it there? The answer is brilliant. It lies in 2 distinct states that we control with the switch. In state 1, the switch is on. This connects the inductor directly across the battery, completely bypassing the capacitor for a moment. It's just like letting our flywheels spin up to full speed freely, without having to fight against the heavy piston. All the battery's energy goes into building a powerful magnetic field in that inductor. And then bam, we hit state 2. We flick the switch off. All of a sudden, the inductor's path to the battery is cut off. Now, if there's one thing an inductor hates, it's a sudden change in current. To keep its current flowing, its magnetic field violently collapses, and it will generate whatever voltage is necessary to shove that current through the only path it has left, which is right into the capacitor. This action adds the inductor's stored energy right on top of the battery's voltage, boosting the capacitor to a level way higher than the source could ever get on its own. And that is the absolute heart of it. By flipping that switch on and off over and over, we can keep charging up the inductor and then dumping that little packet of energy into the capacitor. Each cycle is like another little nudge, pushing that voltage just a bit higher, one step at a time.
Okay, we're almost there. We have a way to ratchet the voltage up, which is fantastic. But there's one last problem we need to solve. How do we stop our now highly charged capacitor from just discharging right back through the circuit the next time we try to charge the inductor?
And the solution? Oh, it's just beautifully simple. A diode. You can think of a diode as the electrical version of a one-way valve, like in a plumbing system. It lets current flow from the inductor into the capacitor, but it slams the door shut if the current ever tries to flow back out. It's the perfect traffic cop for energy flow. So now, with that diode in place, our cycle is complete. It's perfect. Switch on, the inductor charges up. Switch off, the inductor discharges its energy into the capacitor. And that diode? It acts like a one-way gate, trapping that energy safely in the capacitor. By repeating this cycle thousands of times a second, we can maintain a stable, high-voltage output, constantly topping up the capacitor, even while a load is drawing power from it. So now that we have the full intuition, let's just peek at the math. And don't worry, it's surprisingly elegant. This entire behavior that we've just spent all this time describing, well, it can be captured in one simple, powerful little equation. First, though, we have to define the most important control knob we have, something called the duty cycle, which we'll call D. This is just the fraction of time the switch is in the on position during one full on-off cycle. So a duty cycle of 0.5 just means it's on for half the time and off for the other half. Simple as that.
Now, here's the key idea for this all to be stable. Over one full cycle, the average voltage across that inductor has to be 0. Think about it. If it wasn't, the current would just keep building up forever or falling to nothing. That's not stable. This just means that the positive voltage you apply when the switch is on has to be perfectly balanced out by the negative voltage you see when the switch is off.
And when you do the algebra to make those two values cancel each other out, you arrive at this beautiful, beautiful result, the boost converter equation. It says that the ratio of your output voltage to your input voltage is simply 1 divided by 1 minus the duty cycle. That's it. That's the whole thing. So what this means is that you have direct control over the voltage. Just look at this example. If you set your duty cycle to 0.9, meaning the switch is on 90% of the time, the equation tells you your output voltage will be 10 times your input voltage. A 1.5 volt battery magically becomes 15 volts just by controlling how fast you flick a switch. And this brings us to our final mind-bending thought. The ideal equation suggests that as your duty cycle gets closer and closer to 1, or 100%, the output voltage should approach infinity. Now, obviously, that can't happen in the real world. So the question I want to leave you with is this. What real-world imperfections in the wires, in the components, what are the things that actually stop us from achieving that infinite boost?